Okay. All right. Good afternoon, everyone. Let's wrap up our first chapter, first topic for discussion. Okay. Let's see. That one is there. In the previous section, there were a couple of questions that were asked by a student about the meaning of all these symbols. There's right here. So we have this, we define this as a symbol for a diode, right? That's a one-way device. The tip of the arrow has a line running across, perpendicular, if you will. That is noted as the cathode. And the other end is the anode. So in a diode, actually, let's just do this. We have the symbol of a diode this way. This is the anode. This is the cathode. When we refer to diode voltage, anode is always the positive reference. Cathode is always the negative. So diode voltage VD has a positive reference at the anode, negative reference at the cathode. And then the current direction is always from anode towards the cathode. It's a one-way device. Okay, it's a one-way device. Current only flows from anode to the cathode, plus to minus. Okay, so anytime we reference diode voltage, anode is positive, cathode is negative. Diode current, again, anode is positive, cathode is negative. And diode is a one-way device. That's important to note. And this has this one-way device has very important applications when we're trying to convert from AC to DC. Okay, from AC to DC. I'll talk about that in a bit. But is everybody clear? Okay, a diode, anode is always the positive reference, cathode is always the negative reference. More importantly, it's a one-way device. One-way device. So far, so good. All right. So what are applications of diodes? Where diodes are used in multiple, numerous different kinds of circuits, but by far the most important and the most common application of a diode is in converting AC to DC. You've heard me state before, pretty much all all electronic devices that we use, look around us, projector, LED lights, this monitor, writing tablet, smartphones, tablets, laptops, all those computers on the lab benches behind us, all those instruments, everything runs on DC. Okay? Everything runs on DC. There is a power supply inside each and every one of these devices. Okay? We take the ends, let's take our mobile chargers or laptop adapters, for instance. We take those and we plug it into the wall. That's AC. AC goes into that adapter. The output of that adapter goes into our devices, but our devices have DC batteries inside them. So we can't apply AC to them. If you apply AC to them, they're going to get blown out. So the adapter's job is to convert AC into DC. At the front end of every power supply, of every adapter, every mobile charger, at the front end of every single one of those is a diode circuit. And the diode rectifies or diode changes or converts that AC into DC. That process is known as rectification. They use the term rectify as if something was wrong with AC, right? So the process of converting AC to DC is known as a rectification or rectifying The process to convert DC to AC, which is the opposite or the reverse, is known as inversion. So the device that converts, actually, let me write it down. AC to DC it's a rectifier circuit, and DC to AC. Any guesses? You can think back to a solar setup, like a real life solar setup. Yes, inverters, absolutely. It's an inverter. You also mentioned something. Were you mentioning inverter? Okay, yeah, inverters. So you say it's inversion of the rectification process, so inverter. Okay. So all rectifier circuits, all power supplies have a diode at the front end. A diode is a one-way device, and AC goes in both directions. If you feed that to a diode, diode only conducts in one direction. And so we have the preliminary output of a diode circuit is kind of like a half wave or the positive peaks of a AC signal. And then we add a few more components to it and you flatten it out. Okay. So the first circuit is a diode rectifier circuit. And that's the most common application for diodes. Okay. And so this is the symbol for a regular diode. If you have arrows coming out of the diode, that indicates that it is emitting light. Hence, we get LEDs or light emitting diodes. That's the full form for LEDs, light emitting diodes. The flip side of those is a diode that has light fall on it. So you'd say receives light. And these are known as photodiodes. So a diode that emits light is known as a light emitting diode. And a diode that functions based on the operation of light is known as a photodiode. The most common photodiode is a solar cell. The semiconductor solar cell is nothing but a semiconductor diode. Okay. That's a little bit tiny. Let me zoom it up. There you go. So far, so good. All right. Then we have some special purpose diodes. This is known as a Schottky diode. Schottky is named after the person who invented it or created it. Name was, I can't remember the first name, but his last name was Schottky, hence the Schottky diode. Those are special purpose high-speed diodes. They're made out of, instead of being made out of two different semiconductor materials, they are made out of one semiconductor and one metal. Okay. And again, the details of these is something that you will learn in 315. Right now, we're simply looking at diodes and we are simply creating systems with these diodes. So we won't get into too much technical detail. So that's a Schottky diode, which has slight whiskers on its cathode. Then there are other common diodes that look like this. And again, there are whiskers in the form of a Z, and these are known as Zener diodes. Zener diodes have important applications in voltage regulation, in circuit protection, because they operate in the reverse direction. Okay. Normal diodes do not operate in the reverse direction. Zener diodes are specifically formulated and fabricated to operate in the reverse direction. They operated like normal diodes in the forward, the one-way operation, but in reverse operation, there are specific applications for those. And again, that is something that you will study in 315. Okay, any questions? Yes. That's a good question. What does the IS in the diode equation stand for? This IS stands for saturation current. Saturation current is a small amount of current that inherently flows through a diode, the semiconductor material. And again, I will not to brush it off, but technically that would be, again, part of semiconductor device physics 315, which we learned semiconductor devices is at 3 o'clock. You're welcome to attend any of those lectures if you want. Right here in this classroom. All right, let's talk about capacitors and inductors. All right, derivative functions. Now, we talked about wires, right? Wires. A wire is a conductor. So let's see, a wire or a conductor. It's ideal. Both are ideal. The name wire and conductor are synonyms of each other. So a wire inherently has resistance, it has inductance, and it has capacitance. Okay, resistance is noted with uppercase R. And because we are dealing with circuit theory, all analysis is theoretical. And because everything is theoretical, in theoretical analysis, we consider everything as ideal. But in real life, there is nothing that is ideal, right? So resistance is 0 ohms. Inductance, and I'm going to talk about that in just a little bit, is 0. And capacitance is also 0. In real life, this wire would have some resistance, it would have some inductance, it would have some capacitance. Okay. Just going off on a little bit of a tangent. I think I spoke about 100-foot long power extension cable, right? Now, 100-foot long power extension cable, if you plug it into a power outlet, you would expect 120 volts to be available at the power outlet. So 100 feet away, you would still expect it to be 120 volts. But in real life, that 100 feet long or 100-foot long cable would have some resistance, maybe 1 or 2 ohms. So it will affect the voltage that is coming across. That 120 volts might drop to 119 volts, perhaps, or 119.5, whatever, right? I'm just throwing out random numbers here. So it drops from 120 to 119 volts. Yet, if I plug something in at the other end, it will still work because the drop or the interference from that cable resistance is not enough to oppose the operation of that cable. It's not going to affect the operation of the cable. So the resistance is there, the inductance is there, the capacitance is there, but they do not rise to the level that it interferes with the operation. Now, if I had like a USB cable or a HDMI cable that was 100 foot long, well, a USB cable runs on far smaller voltages. It's only 5 volts for power and probably less than that for digital signals. Okay, so the data that is sent over USB cables is very small voltage, very small current. And if you transmit it over 100 foot long, well, now the resistance or the inductance or the capacitance of that cable will rise to the level of interference. Okay, so just a real life thing to keep in mind. All right. All right, so let's come back to our topic. What is an inductor and what is inductance? So if we pass current through a wire, it will establish a weak magnetic field around that conductor. Simply stated, a current carrying conductor will have an established magnetic field around it. That's an observation of physics. Okay. Perhaps you may remember it or recall from your physics classes. Current passes through, establishes a magnetic field. That magnetic field is very, very weak. However, if you take any current carrying conductor or current carrying wire and you wind it up in a loop, one spiral loop, then magnetic field or flux lines go and circle around that loop. If you insert more loops in there, these flux lines will all join up. And so you will get something like this. So you have multiple spirals of that wire. Then magnetic field flux lines join up, they link. And then magnetic field gets a little bit stronger. Okay. And this magnetic field is capable of storing energy. This phenomenon is known as inductance. And this device is known as an inductor. So any current carrying conductor that is wound in a spiral loop, a circular loop, is an inductor. And it stores energy. So it establishes a magnetic field. Stores energy in a magnetic field. That is an inductor. Notation for an inductor is an uppercase L. Unit is named after Henry or H. Typical inductors that are used are millihenry or microhenry range. Milli or micro, right? Millihenry or microhenry. Let's take a pause. Let me know if you have any questions. Any questions at all? Those are just spiral loops of the wire. Oh, those are magnetic flux lines. Good question. Those are magnetic flux lines. So anytime we have a current carrying conductor, it establishes magnetic flux lines around that inductor. I mean, around that conductor. Yeah. So the question being asked was, what were these dotted lines, these dotted circles? And the answer is they represent magnetic flux lines. Yeah, so the magnetic flux lines altogether is, yeah, that's the magnetic field. That's the answer. Yes. So if there are more loops, do they all combine to form one big magnetic field? The answer is yes. So they'll have the individual circles. They'll also form one big circle or one big flux lines. It would appear as if they are flowing in one end and coming out the other. But it kind of is like a, well, not a circle, but like an oval. So it does not actually have a beginning, nor does it have an end. But because it's coming in and out and behaves like a magnet, it has a north pole and it has a south pole. So a magnetic material is something that allows magnetic flux lines to be established within itself with ease. And that's known as a magnetic material. If we insert a magnetic material within that spiral loop, then it makes the magnetic field stronger. And that is the operating principle of an electromagnet. You have a magnetic material that forms or that goes into the core of the inductor. It does nothing until you energize the coil and you allow current to pass through it. Current passes through it. It becomes a very strong magnet. And you're able to lift heavy vehicles with that electromagnet. And that's the operating principle of an electromagnet. Physics at work. All right, so coming back to our discussion. So notation is L, unit is Henry. Typically, they are very small, millihenry or microhenry. And then, oh, this is a symbol, simply a spiral coil. That's the symbol for an inductor. That indicates there are multiple loops. And the mathematical equation is shown here. I'll talk about that in just a bit. Okay. I'm assuming this is all covered in physics classes, right? I mean, the reason I do it is because sometimes the physics classes might have taken place a while ago, so just to refresh everybody's memory. Did you all study these mathematical equations at all in there? No? Okay. All right, so what this equation is displaying is that the voltage for an inductor is directly proportional to the rate of change of current. V is directly proportional to di over dt, time rate derivative or time derivative of the current. The constant of proportionality is the inductance itself. So like Ohm's law, right? V equals to I times R. Here it's L times di over dt. Okay. Is equal to L times di over dt. So why is this equation different? Is it different? No, it's exactly the same. The only thing that's in there is that there are subscripts. Those subscripts have no purpose whatsoever except to indicate which component we are referring to. So if we have a resistor, an inductor, and a capacitor all together in the same circuit, we would note it as VR, IL, or VL, and VC. You're simply saying it's the voltage that belongs to that inductor. That's all this subscript means. This tiny subscript, this tiny L right there, that's what it means. Okay. So this subscript L is simply noting that the voltage belongs to that inductor. That's all it means. If you had multiple inductors like L1, L2, L3, we would say VL1, VL2, VL3. Doesn't have any purpose or meaning beyond that. The off T is sometimes important because if you are talking about voltage as a function of time, That's what that is indicating. So voltage is a function of time. Time is the variable. It could be 0, 1, 2, 3, 4, 5, 6, 7 seconds. It could be 0.1 milliseconds, 0.2 milliseconds, 0.3 milliseconds. It could be any value, depending on the problem or the system. But it simply means that the voltage for that inductor is a function of time. That's all it means. So sometimes, some authors, some books, you will see something like this, or you might see something like this. But they all mean the exact same thing. Okay. All right, what else? If voltage is proportional to derivative of the current, we can find the current by integrating both sides. So you integrate both sides, what do you get? You take L on the other side and you integrate, you get I or IL is equal to 1 over L integral of VL t between 0 to t, where t again is the variable. So inductor voltage is derivative of the current. The inductor current is the integral of the voltage. You simply sum up the voltage slices from 0 to t. That t is a variable, meaning if you are analyzing the circuit for half a second, it would go from 0 to 0.5. Again, we won't look at that right now. We'll look at it later. Okay. So now physically think about what happens. You have an inductor, you're passing current through it. Inductor is nothing but a wire, right? If you pass current through a wire, what is the wire behaving like? It is behaving like a short circuit. If I take any of the cables that I have, if I have this USB cable here, it's supposed to just transmit voltage or current, right? Is it going to change anything if I wind it up in a loop like this? Yes and no. This is an inductor. Plus, it has current carrying conductor that is separated by insulating material, so it also is a capacitor. But you wind up a wire or a cable in a loop, it's an inductor. Okay, but signal is still going to be transmitted. It's not going to stop. Point here is that just because we take a wire, we wind it up in a spiral loop, it's not going to change its resistance. The resistance is 0, it will stay 0. However, what happens is, let's say you have current flowing through the inductor. That current is flowing from right, well, my right, but your left to right. Okay. So for instance, let's do this. Current IL flows from left to right. When it flows from left to right, inductor is a passive component. So where is the plus sign? Is it on the left or is it on the right? And again, important concept. Current is like any other quantity. If you have water in one end of the pipe and you lift up one end, which direction is the water flowing? From high to low. Temperature also flows from high to low. If you have high temperature region and you have a low temperature region, high temperature will go towards the low temperature region. Pressure, the same thing. High pressure regions will create conditions where it goes from high to low. Electrical energy, same way, goes from high to low. So if the current is flowing from left to right, this end is higher, this end is lower. So plus on the left, minus on the right. All components which are loads like resistors, inductors, capacitors, everything else, so I mean, all of those have current that follows this principle, except for a source. A source supplies energy. So in a source, we model the current as going from minus to plus, not plus to minus. Okay, from minus to plus. That's just a separate topic, but I figured I'd mention it right now. Okay, so if IL is flowing from left to right, VL, the voltage across the inductor, is plus on the left, minus on the right. Okay. Technically, if IL is flowing, resistance R is equal to 0. But let's say IL starts flowing, it's supplying some energy to that inductor. The inductor receives the energy and stores it. Okay. While it's receiving the energy, there might be some opposition. But what happens is the magnetic field is established, and that magnetic field gives rise to an EMF or electromotive force or voltage that opposes or is in opposition to VL. So the polarity of that would be something like this. So that magnetic field gives rise to a voltage that essentially opposes any change in the current. So a very simplistic explanation, if you will. Okay. As long as IL doesn't try to change, this voltage will not oppose it because it's stored the energy. Let's say IL is equal to 1 amp. Okay, 1 amp. 1 amp is flowing in there. It starts receiving the energy. The stored energy at some point will reach 1 amp in that inductor, okay, in that magnetic field. So once it reaches 1 amp, that inductor behaves like a short circuit. R is equal to 0. And that is what you're going to get mathematically here. You have a derivative of IL if I remains constant, not AC, just DC. If I remains constant, well, mathematically what happens? Derivative of a constant is 0. So voltage across the inductor goes to 0. Voltage across the inductor goes to 0 because it behaves like a short circuit. So the answer to this question is that the voltage across the inductor will go to 0 when the current is constant. We see that mathematically, and the mathematical observation, of course, is based on physical fact. And so inductor is or behaves like a short circuit. And that is when it stores as much energy as it can. What time is it? 2:43. That makes sense? One other thing that is not something that we'll look at in this class now, but you will learn about it in the future, especially I think you'll look at it in 2:15, I believe, next quarter, is the charging and discharging phase. So inductors and then capacitors, which is on the next slide, they are both energy storage devices. Inductors store energy in the magnetic field. Capacitors store it in an electric field. So when they receive the energy from the source, we say that they are being charged up. And then they release the energy back into the circuit, we say that they are discharging. So there's a process. There's a charging and discharging, Depending on the circuit, depending on the design, depending on the size of the inductor and capacitor, the charging and discharging can be fast or can be very, very slow. But it is not in an instant. We can't flip a switch and have all of that energy just rush into an inductor or capacitor all at once. It takes a finite amount of time. That's again physical fact, and there are mathematical equations that describe this charging and discharging. Those are known as transient analysis. Okay. Thanos could have all the infinity stones in the world he wants, and he can snap all his fingers all he wants. All of that energy is never released all at once. It takes a finite amount of time for the energy to be received in and to be discharged. Okay. So we are not talking about that portion, charging and discharging. We're not talking about that right now. When we say constant current, we are simply saying we apply DC to it. When we apply DC to it, once it reaches full charge, it behaves like a short circuit. All right. What was I saying? Oh, yeah, full charge. So voltage is equal to 0 if I is constant. And at this point, we say it is fully charged. Fully charged. All right, I have 15, or actually 14 minutes left. Let's move on to the next, which is capacitor. Yes, go ahead. This one? This or this? Okay, all of it. All right, so primary mathematical equation or relationship is that voltage across the inductor is directly proportional to the derivative of the current. So V is directly proportional to di over dt. The constant of proportionality is L, the inductor. And so we get this equation right here. V equals L di over dt. That is the primary VI equation for an inductor. This right here is simply the notation. So this subscript L that we see here simply indicates that the L belongs to that specific inductor. That's all it means. Doesn't mean anything else. No. If you have a circuit and the circuit has a resistor R, inductor L, and it's basically the name of that inductor. That's all. Instead of VL of T, if the inductor was named Batman, you would say V Batman of T. Does everybody get that? You could call that inductor whatever you want. It could be L1, L2, L3. You would say VL1, VL2. And then this, the T inside the bracket, meaning it's a function, that voltage is a function of time. So if time changes, the voltage has a different value. Yes. That's for current. Lowercase I is for current. Yes. No, that's for the voltage across the. So the question being asked is about this. No, this one, right? This one is the voltage that is caused due to the magnetic field. Yeah. Again, that has no, that is not VL. VL is at the top. This is opposing force due to the magnetic field. All right. No, it doesn't change VL to 0. That opposing force opposes the current from changing. It opposes the input current from changing. Okay. All right. Let's see. We'll have 11 minutes. All right. Capacitor. Capacitor and inductor in many ways are very similar to each other. And in many ways, they are completely opposite. So one of the primary ways they are very similar is that they're both energy storage devices. Okay, they're both energy storage devices. Inductors store energy in a magnetic field. Capacitors store energy in an electric field. If you take any two conducting parallel plates and you hold them in close proximity, separated by an insulating material, they form a capacitance, or they form a capacitor. As the name suggests, it is the capacity to store charge. Okay, you can take the two palms of your hands together, put them together, they're separated by air. Technically, it's two conductors separated by an insulating material, and you have a capacitance between the two palms, two hands. Okay, very, very small, but it's there. So a capacitor is nothing but two parallel plates or two conducting plates separated by insulating material. So if you have two rectangular plates crossing over each other, then the places where they overlap is where you have your capacitor. Capacitor symbol is two horizontal lines in or not two horizontal, two parallel lines separated by a small distance, which is given here. So noted by uppercase C. Units named after Michael Faraday. So 1 farad, F-A-R-A-D. And typically capacitors are in micro, nano, picofarads and small. Typically are micro and nanofarads. Okay, micro and nanofarads. So I'll do a quick explanation of how a capacitor would work. This is the symbol for a battery, by the way. Okay, yeah, one long line and another parallel line that is shorter. The longer one notes the positive end of the battery. The shorter one notes the negative end of the battery. If you connect a battery to a capacitor, what happens? Capacitor does not have any charge initially across its plates, completely discharged, 0 volts. Well, these plates are conducting, so they are more often than not, they might be made out of some sort of metal. And because they're made out of metal, they have some free electrons. Those electrons get attracted by the positive charge. So electrons move in this direction. When an electron moves out of its atom, it leaves behind its nucleus. It's an ionized atom. It leaves behind a nucleus, meaning the empty spot or the hole is now associated with a positive charge. So positive charges build up on that plate. On the other side, the negative end of the battery repels the electrons, and the electrons moving in that direction. And so negative charges build up on the other side of the plate. The difference in the charges results in a voltage that appears across the capacitor that is known as VC. At some point, VC is going to equal the supply voltage VS. Let's call this VS. And when VC, the capacitor voltage, equals that supply voltage VS, we say that the capacitor has reached full charge. It has stored as much energy as it can, 100% capacity. And when that happens, there is no more flow of electrons. And because there is no more flow of electrons, we say that current is not flowing. And so at this point, we say current is equal to 0, or capacitor current is equal to 0. What is the most important point that you note about this? You have electrons flowing. When electrons flow in a circuit, we say current is flowing. So what do you notice about the flow of electrons? It stops. Well, yeah, it stops, but it stops at the plates of the capacitor. Remember, the key word for a capacitor is that it's separated by an insulating material. So physically, there are no electrons that can go across the plates. Okay, there are no electrons that can go across the plates. They are simply moving between the wires that way. But it's still moving, even though it's separated by the plates and the insulator here, right here, right? No electrons can flow across the plates. Yet we still say current is flowing through the capacitor. So keep that in mind. Physically, current is not actually going through, but technically we say current is flowing through the capacitor, or we refer to it as capacitor current. I provide this explanation just so that students have the basic physical or the physics-based explanation, right? You have two plates, then the question automatically comes up. If there are two plates and they're separated, how is it that current is flowing through? The answer is physically, there are electrons that are not flowing through, but it's the movement of electrons in the circuit. The electrons are continuously flowing, right? That's not going to stop. And the movement of those electrons, we say, is capacitor current. Yes. So the question being asked is if the movement of electrons will stop in the entire circuit. Well, it depends on, the answer is that it depends on the circuit. If it's a simple circuit like this one, where you have a voltage source and a capacitor and nothing else, then yes, it will stop. There was another question someone had. Okay. Yes. So the question being asked is what happens to the electrons that are creating the charge on top of the plates, right? Good question. So the capacitor will store the energy. As long as the source is connected, the capacitor will store the energy. Now, theoretically speaking, if we remove this charged capacitor from the circuit, the charged capacitor should be able to hold or store that energy to the end of time. But again, remember the keyword, we don't have an ideal component in the real world. It's never ideal. So depending on the size of the capacitor, depending on the insulation between the distance between the plates, it'll slowly discharge either through the air or through that insulating material itself. Capacitors, we have to remember, the capacitors are very, very tiny. So the amount of charge they store is also very tiny. But there are videos in the internet that you can look up. People will charge up huge capacitors. So it's a large amount of energy that is stored, remove it from a circuit, and then you short those two leads together. What happens then? Remember the example I gave about the battery terminals being shorted out? So what do you think happens? All of that energy is released in an instant. So there'll be a spark. But once you have the spark, the capacitor is now drained. Done. So if you have a very, very tiny capacitor and you charge it and you just short its terminals, chances are you won't even see that spark. Right? Because most capacitors are very small. But if you take like a huge capacitor, like there are capacitors that are huge, like a big cylinder, and you take that, it has a large amount of energy stored, you short its terminals, you have a big spark. Okay. Still have a couple of minutes. So if you have to leave, you can leave. I just want to finish this up, okay? The mathematical equation. So the mathematical equation here is that capacitor current I is directly proportional to the derivative of the voltage. So I is proportional to dV over dt. The constant of proportionality is the capacitor itself. So capacitor current I is C times dV over dt. Capacitor current is the time rate derivative of the voltage, applied voltage. If you want to find the voltage from the current, then you integrate both sides, and capacitor voltage is integral of the current, flip side. So those are the VI and IV equations for both a inductor and capacitor. Also, what it means when it's fully charged. If V voltage is a constant, meaning a DC voltage is applied, just mathematically, if V is constant, what is I? 0, right? That occurs when the capacitor reaches full charge. When Vc equals Vs, it reaches full charge. Electrons no longer flow through the circuit. Voltage across the capacitor is fully charged, but the current stops flowing. I is equal to 0. And we can see that mathematically also, right? So if V is constant, I equals 0, we say capacitor is fully charged, and it behaves like an open circuit, the opposite of a inductor. All right. Actually, I got done in time, and just a minute over time, right? So if you have questions, feel free to ask. We still have a few more minutes before my next class, but officially I'm going to say class is at an end. I will see you all on Monday. Monday is going to be quiz 1. Quiz 1 is based only on the material we have done in the lecture. Okay, so Monday, Wednesday, Friday, we had 3 lectures. The material that we have covered in the lecture is the only thing that I will assess on that quiz. There's no online option for the quiz. So if you are thinking of attending online, there is no online option. So you do not want to miss it. All right.